Hello, everybody. So the last time we met, we very quickly got a taste, a glimpse of the command that we use in Mathematica to plot functions of two variables and produce three-dimensional surfaces. So today I'm going to spend more or less the whole discussion period showing you various ways that you can manipulate and add important functionality to your three-dimensional plots. Okay, and we're going to use the same function at the start as we did last time, and that function is going to be the wave function for a two-dimensional particle in a box. And so here's what it looks like. It's a function of x and y, and then there's some indices, and these are the quantum numbers for that indicate which state the motion in x and y are in. And so this function looks like this: sine nx pi x over L, and then sine ny pi y over L. Okay, and we're going to set, just makes it a little easier, we'll just set L equal 1 in both, so that it's a square box with L equal 1. Okay, so let's go ahead and type that in, and then we'll start playing around with the three-dimensional plots. So psi of x and y, so we need underscores, defining a function, and then colon equals 2 times sine nx star pi star x, I'll leave out the L since it's 1, and then times sine ny times pi, times y. All right. So there's our function. And now what I'm going to do is plot that function. So plot 3D is the name of the command. And then I'm going to say psi of x and y. And now what I'm going to do is I'm actually going to use replacement rules to specify the quantum numbers nx and ny. So we'll have an easy way to modify them. And so for replacement rule, I say slash dot. And then since I'm going to have two at once, I'm going to put them in the curly brackets, a list. So I'm going to say nx arrow 1, and then ny arrow 1. Okay, so that will plot the ground state wave function, and then I have to put in my ranges of x and y, and so I'll say x goes from 0 to 1, and y goes from 0 to 1. Okay, so now we can enter that, and you see we get a plot. Now, what do I want to say? There's lots of things to say about this. So first of all, in these 3D plots, it may not be, especially because the ranges are the same here for both dimensions, it's not obvious what the x and y axes are. Okay, it's pretty obvious that the vertical one is the function axis. So let's go ahead and put some axes labels on there. And the way we do that is the same way as in the plot command. So we say axes label arrow, and now we can put in 3 labels. So I'll say x and y and psi. Okay, so go ahead and let that rip, and now we see that the x-axis is the one closest to us, and then y is over there. Now, I wanted to use this as an opportunity to tell you that I know a lot of you open up the notes, which I think is great, and you look at them while we're doing things in the class. But I also know that some of you fall behind because you're typing everything that's in the notes. And I often am doing shortcuts here. I'm not typing all the details. Those are there for you to see more details. But oftentimes while we're working together in the lecture or the discussion, I don't type everything that's there. Another thing is that this is not a super complicated plot command, but I think it's always a very good idea when you're entering commands in Mathematica to start with the simplest version of that command that's going to give you an opportunity to check and see if you have it right, and then add options. Because sometimes you type in a very complicated long command, you're missing a comma or have the wrong kind of bracket, or there's just something small wrong. It's hard to see when you have a huge long command. So for example, in this one, I generated the plot, and then I added the axes. And then we'll be adding more options as time goes on. But as soon as I generated the plot, I knew that I had the basic plot was OK. OK. Now, let's play around with this a little bit. The nice thing about having this particle in box wave function typed in now is that we can actually explore some of its properties. So this is the ground state. Suppose I wanted to find out what's the probability of finding the particle in the box when it's in the ground state. What does that probability distribution look like? Well, those of you who are in Chem 131A now know that Max Born told us that the proper way to interpret the wave function is that if you square it, that gives you the probability density of finding the particle. All right, so we could square this guy here. So mouse that in. And actually, we don't need the definition of psi. We already have that. And so we could just very simply change psi to psi squared. And if we re-enter that, it's not too surprising that the probability density looks a lot like the function itself, okay? Because this function is positive everywhere, so is the probability density. All right, but what happens if we change the quantum state? So if I go up here, for example, and I put in, instead of the ground state, 1, 1, I put in, let's say, 2, 3. So we'll have 2 quanta in the x direction and 3 in the y. And then you see that you have a more interesting looking function, where in the x direction now we have a complete cycle of the sign, and in the y direction we have 1.5 there. Okay? So you can kind of see what adding more energy in these degrees of freedom does. It produces more oscillations in the wave function. Okay? So if we go down here now and look at the probability for the same one, notice here the amplitude goes plus and minus. When we square the probability, square the wave function to get the probability, we'll get a positive everywhere function, where now we can see that there's an interesting nodal structure. So for example, the particle will not be able to be anywhere in here along the x-axis in the middle of the box. And then there's 2 nodes in the y direction. Okay, so this quantum particle is, if you like, enhanced at certain regions of the box, and forbidden from being other places in the box. And having the ability to look at the wave function using a simple plotting command in Mathematica helps us to appreciate the quantum behavior of this particle. Okay, now actually, if we wanted to be a little more accurate here, in our labels, we could say prob dense or something like that. That's the square of the wave function. Okay, now a few other things to point out. So one is that by default, when you make a three-dimensional plot, a certain coloring scheme is used. That coloring scheme is called lake colors, and it's a fairly attractive one in my opinion. We'll see how to change that in a moment, and I encourage you all to use your favorite color schemes. There's a lot of really nice ones. Another thing is that the default is to put a grid on the function. The grid's kind of useful to help you to be able to follow the behavior of the function. We'll see that you can modify that and get rid of it altogether if you wish. And then another thing I want to point out is that Mathematica decides based on the behavior of the function as it's calculating it. So it evaluates that function and draws it. It decides, you know, how. Well, actually, yeah, it decides how coarse or fine to evaluate the function as it's making the plot. Now, this particular representation is pretty nice. This is a fairly oscillatory function, and you can see if you look on the places where it's turning around, where it's kind of sharp, it does a reasonably good job of catching that shape very accurately. But if for some reason you want to make it either more or less resolved, this is something that you have control over. Okay, so I'll show you how to manipulate the coarseness or fineness of the plot. So the default is, I believe, to use 17 points along each dimension to draw the function. Now, if you wanted, for some reason, if you had a very complicated function and you wanted it to be displayed relatively quickly so you can see if it looks right, you could actually decrease the resolution by changing the grid. And so the command to do that, it's an option, it's called plot points. And you put arrow, and then you say how many points you want to use along each direction. Okay, so for example, if I put 10, what that's going to do is that's actually going to decrease the resolution of the display here because I'm using less points to represent the function. All right, so you can kind of see that it's got a little more of a sort of roughness to it, and you can also see that the grid lines have been changed. Suppose you wanted to make a finer version of the plot. Well, then you can increase the plot points. And so, for example, if I change to 40, you see it takes a little longer, but now I think you can see that this function is plotted very, very smoothly compared to when we only had 10 points. Okay, so what about now the mesh? Suppose you wanted to make the mesh finer as well. Well, there is another option, which is called mesh with an arrow. Okay, and this gives you the number of lines that are drawn in each direction. Okay, so we put mesh equal 40, and now you see we have a much finer mesh. And that may be something that you want to add to your plot. Now this particular function, just the way it's colored, it actually looks pretty good, and you don't need a mesh to really see quite well what the behavior of the function is. So you may want to actually get rid of the mesh, and the way you can do that is just turn it off by saying mesh goes to none. Okay, so if you do that, now you see you've got the surface drawn and colored nicely, but there's no mesh drawn. All right. Now, I mentioned that you have control over the coloring schemes, so I'm going to go ahead and get rid of this plot points. We'll go back to the default, and then we'll play around with the colors. Okay, so just re-enter that. You see now it's a little rougher. All right, so to see what kind of colors you have available to you, you can go to the Documentation Center. And if you type in color schemes, the first thing that comes up there is a guide on the various color schemes. And so what you have down here now is a list of all the predefined color schemes, and some of them are very attractive, some not so much. And basically the way these will be used is if you change to one of these color schemes, the lowest value of the plot will be plotted with whatever the color is on the left end of the bar and the highest at the right end. Okay, so for example, suppose I go back to this plot, and I'll go ahead and put the mesh back in by removing that option. I could change the color scheme from the default, which is the lake colors, by adding the option color function, and then an arrow, and then I give the name of the scheme that I want. So for example, maybe I want to use mint colors. Let's see what that looks like. So I type in mint colors and see what we get. That's kind of nice. What else? How about fuchsia tones? Oops, I guess I misspelled it. Where is it? Oh, fuchsia. Okay. Ah, I have this S in the wrong spot. All right. There you go. So that's kind of nice. A little more noir-ish. Anyway, the point here is that there's lots of really nice color schemes here, and you could waste a lot of time checking them all out and finding the ones that appeal most to your aesthetic sensibilities. In general, I will not micromanage you on this, and I encourage you to play around and make your plots look nice by choosing a color scheme that you like. The default is always fine. Okay. All right, so let's see. Another one that's, I'll just point out one more, that's nice. Remember that it's occasionally useful to be able to do black and white plots. And so there is a version of the color scheme that is appropriate for black and white. It's called gray tones. And so now you can see that the lowest value of the function is plotted with the darkest black, and then there's a gradation toward white. Okay. Now there's other things that you can do. I'm just going to, in fact, there are many, many things that you can do. So you notice this surface is kind of drawn like matte. It's, you know, you can kind of see that there's a light shining on it to give you some good depth perception. But the actual surface itself is kind of it's not shiny, right? It looks kind of like a matte photograph. You can actually change the surface characteristics, and so I'll just show you one example. This will be kind of nice when we're displaying orbitals, which we'll do probably next time. So let's see how we can make a couple of different kinds of surfaces. So the first thing I want to show you is let's make the surface more see-through. Okay, so what I'm going to do, I'm actually going to use the wave function itself for this. All right, so we put this back, and I'm just going to re-enter it. Okay. Now, notice that the orientation's pretty nice. You can tell that there's a hump here and that there's a valley behind it. All right, but the valley is somewhat obscured by the fact that this surface here you can't see through it. Right, it's opaque. All right, So you may want to reduce the opacity so that you can see through it, partly. Maybe that will be important for depicting whatever it is that you're trying to depict with the surface. All right, so there is an option here called opacity. And, sorry, its plot style goes to opacity, plot style arrow, opacity. And then within square brackets, you put a number. So let's put, to start, 0.5. And this number is between 0 and 1. Okay? So now notice the surface is see-through. Okay? And maybe it's even more confusing now, but in any case, we've made it see-through. So to get a feeling for what opacity is, let's crank it up a little bit. Let's say 0.8. You can see that the larger the number of opacity, the more opaque the surface becomes. And if you go to really small values, it becomes practically transparent, completely transparent. All right, so that's something you could play with if you want to be able to see through your surface. All right, now what if you want to take it to the other extreme and make a surface that you can't see through? So if I copy that, I'm going to get rid of this one. And for this version, I'm going to get rid of the mesh. Mesh goes to none. And then I'm going to change the characteristics of the surface in a couple of different ways. Okay, so the first, and the way I'm going to enclose these couple of different ways, and this is a strange syntax, so if you ever want to do it, just look to the example and play around with the options. I'm going to use what's called a directive. And within this directive, I can change things more than one thing at a time. So the first thing I can specify if I want is the color. So I'm going to put in pink. And then the next thing I'm going to specify is a quantity called specularity. And roughly speaking, this is a measure of the shininess of the surface. Okay? And so what I can put in specularity are a couple of options, one of which is the light color. All right, so it's going to be white light. And then the second is a number, which basically indicates the shininess. Okay, and this number, its default is around 1, I think it's 1.5. But the higher the number you put in, the more shiny it is. So I'm going to start with a big number, 100. Okay, and so now, let's see, we need one more bracket. And then let's see what happens if we enter that. So now, notice you get what looks to be a nice solid surface. And you can really see where the light is hitting it by where you have the reflections. And you can change the specularity to get a feeling for what it's like. So suppose we reduce it now to 10. You see the appearance of the light on the surface is kind of spread out. It's not as, it doesn't look as sharply focused. And if you go back to, say, 1.5, which is the default, oops, not 11.5, you get a very kind of washed out looking object. So if you crank it up, you get this really nice feeling of a solid surface with a bright light hitting it in very tightly focused areas. All right. Now, another thing that you may want to do is you may want to change what's called the point of view. Okay? So notice that every time we do a three-dimensional plot, we're always sort of looking at it with the axes oriented in a particular way. And what that means is that we're out here looking at the surface at a particular set of coordinates. And I don't remember what the default value is for the coordinates, but I do know that you can play around with that and change it. And the way you do that is you actually put in the set of coordinates for the observer. So for example, the way you do that is you say viewpoint, and then you put an arrow, and then you need to give your x, y, and z coordinates. So if I say x2, y2, and z1, you can see that now I'm basically looking along the bisector of the xy axes, and I'm a little bit elevated off the surface, which it's 0 here. All right, and you can modify that and see what it does. So I could put, say, 2 to 4 here. Now I'm more looking at it from more at the top, and you can change these guys here and see what they do. Okay, so those are all possibilities for making your surface more informative. You could also, of course, use the left mouse to play around with it by hand. You don't need to just set the viewpoint. All right. Okay. Now, so as I've mentioned already, there are many things that you can play around with, and we've hardly scratched the surface here. So if you have any interest in finding other interesting features that you may wish to add to your 3D plots, you should consult the Documentation Center. Now the next thing that I want to do is to introduce you to another way of depicting three-dimensional functions, and that's through what is called a contour plot. Okay? And so what is a contour plot? Does anybody know what a contour plot is? Has anybody seen a topographical map? A topographical map is an example of a contour plot. And essentially what it is it's defined in terms of sets of numbers that define lines of constant values of the function. Okay, so one contour in a three-dimensional function would have the form f of x and y is equal to a number, a constant. Another contour would have f of x, y equal to a different constant. So by drawing a series of these so-called level sets, once you get used to looking at these plots, and most of you probably have used topographical maps, so you know how that works, then it's another informative way of being able to see the features present in a three-dimensional surface. All right, so I'm going to introduce that to you now, and we'll go ahead and go back to our simple plot here, and then I'm going to replace plot 3D, and I'm also going to get rid of the Z, because what we're going to see here is that it's a two-dimensional representation of a three-dimensional plot. Okay? All right. So the name of the command is contour plot. Okay, so if we enter this, now you see we have a different representation of our function. You can see, if you're familiar with contour plots, you can see that obviously it has peaks and valleys. So typically the way the coloring's done, this is the lake color scheme. The default scheme is that the lightest color in the lake colors will be the smallest values, or in this case, most negative values, and then the darkest colors are the most positive values. So you can see here we have a hole, a peak, and a hole, and we can see that we have nodes in between each of these features. All right, so this is another way of depicting the behavior of that function, this time in terms of its level sets, which are drawn here with lines around them. Okay? Now, as with many things in Mathematica, there's a certain default number for how many of these contour lines are drawn, and that's something that you have control over, as well as the style with which the contours are drawn. So suppose we wanted a little more resolution. Then we can increase the number of contours. All right, and I'm not sure what the default is, but it may also be something like 11. But in any case, you can change it. So you say contours, arrow, and then you put in the number that you want. Okay, so if I wanted to increase that, I could put in, say, 20. And now you see there's a lot more contours drawn here. So that's the number of contours between the highest and the lowest values of the function. Suppose you wanted to make the lines dashed lines. Then you can add an option contour style, arrow, dashed. And so now you can see that you have dashed lines. All right. Now, another thing we can do, which is sometimes useful, because notice we don't have a z-axis, so it's not obvious here what we're plotting. And also notice that when I have the axes label option in this command, I don't get any axes label. Well, the reason for that is because this type of plot is similar to what we saw when we did plotting two-dimensional functions. It's considered to be a framed plot, and it seems strange maybe, but if you have a framed plot and you want to put in labels, you have to use a different option. So axes label doesn't work. What you have to put in is frame label. Okay, and so if you do that, now you see you have X and Y labels on your axes. Okay. Now another thing, we don't have Z, as I said, so if we want to say what it is we're plotting, we may wish to include a title of our plot. Okay. So the way you do that is you put in the option plot label, arrow, and then the string, your title. So I might say 2D particle in a box wave function. All right, so now I have an informative title to my plot. Okay, now another thing about contour plots is, because we don't have the z-axis explicitly shown for us, we don't really have an accurate indication of what are the values. Okay? We can see that the most negative values are drawn white, and then as they become more and more positive, they get more and more color. And then the positive features start out sort of in the middle of the spectrum and become darker and darker blue as we go up in positive values. But we don't really know how the color variation is mapped onto the values of the function. And so in contour plots, it's especially useful to add a legend. All right? And the legend for contour plots is a bit more complicated than that for an XY plot. And I'm going to show you how to do it, and to show you a couple of things that you can change in the legend. But it's a very non-intuitive command, and so this is a very good example of a case where having an example sitting in front of you is the best way to actually get it right. Okay? So another thing I want to remind you of is that when we want to put in a legend to our plots, we need to load a package, because legends are not part of the default machinery that's loaded in when we fire up Mathematica. All right, so let's go ahead and do that. So we say less than, and then the name of the package, plot legends, and then backward single quote, and then we can enter that. And we can have a look to see if we got it. dollar packages, and now we see that in fact we have plot legends loaded in. Okay, now when we were doing the two-dimensional plots, it was pretty easy to add a legend, right? We just added an option within the plot command. For contour plots, it's substantially more complicated. So the first thing that we have to do is we're going to use the legend in a different way. We're going to include in our plot command what I call a wrapper. So this is a command that's going to be wrapped around the plot command, sort of like animate, what we did last time. And the command is called show legend. Okay, and then we're going to put something inside. So inside this is going to be the command specifying the plot that we want the legend for. Okay, so I'm just going to go up here and grab this guy. And I'll go ahead and just use the plain old default here with some labels for the axes. Let's see. So grab that, put it in down here, and then I'm going to put a bracket at the end. Okay? So you see the show legend is wrapped around the contour plot. All right, now we're not done, not even close. So one thing we need to specify is the color scheme that's going to be used for the legend. And I think it goes without saying the color scheme should be the same as the scheme that you're making the plot. Okay, so the default color scheme is called lake colors. All right, so what I'm going to do to specify that is put in this curly bracket with a specification color data, and then within that the name of the color scheme. So it's lake colors. Okay, and bracket. And now there's a very funny construction that's basically just instructing Mathematica how to draw the graphics object that's going to ultimately be our legend. Okay? And I won't say much more about it except that you have to put it in as I'm doing it now, or your legend will be screwed up. Okay, so there's a funny little thing that's got a square bracket, and then 1 minus pound sign 1, and then a square bracket, and then a space, ampersand. All right? Just remember, you can always look at an example, and you should type it just like this. Okay. Now, the next thing we do is we put in how many different slabs do we want to represent in our legend. And this will be obvious once we do it. I'll show you what this number means. So I'm going to put in 11. So this means my legend is going to have 11 different colors spanning the range of the function. Okay? And then I put in the upper and lower limits of my function. So here you need to know something about your function. And you may recall when we plotted the 3D plots, we can see that our function goes between -2 and 2. Okay? So I'm going to put those limits in now. And they're in quotes because they're going to be used as labels on the legend. I'm going to start with 2. That's the maximum value. And then -2. Okay? All right. Now we should be good to go. Let's hit enter. And we see that something's wrong.
You just missed that curly bracket.
I missed a curly bracket, did I? Where should have I put that? I should put that here. Thank you. All right. Okay, so now you see you have a legend. Okay? And notice a couple of things. Oh, sorry, I was saying something wrong before. The lightest colors are actually the most positive. Okay? Sorry about that. That's right, because the sine wave goes like that. Okay. Well, now we can see, right? It shows you legends are important, because I was guessing incorrectly the values of the function. Now I know for sure. All right, the lightest colors are the most positive, and then they go to the darkest colors, most negative. All right, now the other thing is, what's the 11? Okay, the 11 is the number of different colors I have here. So if you wanted, you could change that. You could say, put it to 5 or something. Okay, and now you see you only have 5. Okay, now a couple of other things. This is a really inconvenient spot for the legend, right? This happens in general. We saw this already with the two-dimensional plots. So let's move it so we can now add within our wrapper the legend position, arrow, and I played around with this one and found that 1.1 and minus 0.4 looked good to me, so that's what I'm going to put in. Whoops, we don't need a quotes here. I don't know why I have that quote. All right, and so now if we re-enter, nothing happened. Oh, the problem is this is outside the curly bracket. Sorry about that. So Control X and put it in here. So Control V. All right, now it should work. And there you have it. Okay, so that's a much nicer place for the legend. Now, what else about the legend? Well, suppose you want to get rid of the shadow. You can say with another option inside the curly bracket here, legend, shadow, arrow, none, which I prefer personally. And so now you see the shadow is gone. Okay, what else? Another thing is you may want to change the size of the legend. All right, so let's go back to 11 here and enter that. Notice the legend's, you know, maybe a little too small for your taste. Well, if you want to crank up the size, you can say legend size, arrow, let's say 1.5. Now you see it draws it bigger, and in this case then you may want to change the position a little bit, say to minus 0.6 or something in the Y direction so it's more centered. Okay, so now we have a rather nice looking plot. Suppose you want to change the color scheme. All right, so I'm going to change it to something I'm going to call fruit punch colors, which is one of my favorites. So now what we have to do is we go back within our plot command here. See, it ends here, and we add an option to the plot. All right, so we say color data bracket, and then put in the name. So I'm going to say fruit, punch colors. Okay, and let's go ahead and enter that one. Oops, wow. Oh, the problem is it doesn't need the brackets. Sorry. I'm getting all confused with my complicated. The color data is for the legend. What we need to do is say color function goes to. Sorry. All right. All right. Now, if you do that, notice you got a nice different color scheme for the plot, but you have to also remember to make your legend consistent with the plot. All right. So we have to put in fruit punch colors in both places to make them consistent. All right. And so now if you do that, you have a lovely looking plot with a slightly more, let's say, bold color scheme. Okay? All right. Now, I'm going to finish up just in the last minute or two here with a variation on the contour plot, which is actually quite nice for plotting functions of the sort that we're plotting here. And this type of plot is called a density plot. And I think the best way to see how that works is just to make one. So if I go in here and change contour to density and enter it, notice I get this kind of fuzzed up version of a contour plot. Okay, it's exactly the same function, same information. We have, the same legend. But you notice there's a subtle difference here, right? I mean, it doesn't have these sort of pretty obvious demarcations. It's kind of fuzzed out. And this is a particularly nice way of drawing functions that represent quantum objects, because as we learn very early on when we're learning about quantum mechanics is that you don't talk about where a particle is with great precision because of the uncertainty principle. And so often we're looking at things like probability densities or the amplitude of a wave function. And it's kind of a nice way to help you to remember that about this uncertainty if you have a plot like this, which kind of gives you this fuzzy quantum particle look to it. Okay? So that's the density plot. Very, very similar in all respects to the contour plot, except without the demarcations. Let's just go back to contour so you can see the subtle difference. All right. So notice we have these lines. If you could get rid of the lines by saying contours, arrow, none. Oops, what was that command? Contour style. Contour style. Okay. But still, you see, you have this sort of, each contour is drawn in a different color, whereas in the density plot, there's sort of a smoother variation between the colors. I have to get rid of this guy now. Okay, so that's another way to do more or less the same thing, but in a slightly different way that for a problem like this might actually be more appealing. Okay, so that wraps it up for today. What we're going to do next time is we're going to see how to plot four-dimensional functions. Okay, so something to look forward to. See you tomorrow.